Hello, my name is Erik Lindskog and I am going to present the paper REEFT-360 Real-Time Emulation and Evaluation Framework for Tilebase 360-degree streaming under time-varying conditions. But before we start, I'm going to introduce myself quickly. So my name is Erik Lindskog. I took my master's degree at Linköping University and I'm currently working at Nordeus Group in Linköping. So 360-degree video is very different from regular video in that they're very large and they consume a lot of bandwidth because most of the transfer data is not used in that. You have the viewport, as can be seen here, which is not the entire video. So there's a lot of video that is not being viewed by the viewer and is as such wasted. The viewer can, however, move around and look at different parts of the video. So this is a problem naturally because you want this viewport here to have the same quality as a standard video, meaning that the resolution needs to be very high and this consumes a lot of bandwidth, as said. So a lot of papers have considered solutions for this and they mostly include advanced prefetching method algorithms, specialized video encoding that allows you to have separate videos where some areas of the video are in low resolution while you have an expected quality enhanced region that has the highest or higher resolution. And most of them utilize the small viewport in some way, as it is the main limitation and thus you can use it. So one prominent solution is tiled 360-degree video, where you split the video into separate parts. So effectively, in this case, you'd have 5 videos or 5 separate streams, allowing you to fetch the streams separately in different qualities. For example, here you'd have the one that's right below the viewport be in the high quality, while the ones next to it being in medium, and the ones that are outside being low quality. So this allows the bandwidth to be spent more wisely, as you can put the bandwidth into the parts of the scene where the viewer is actually looking and not waste it on the other parts. And this introduces problems, however, naturally, as if a viewer changes their direction in a current chunk of video. So if you fetch a chunk of video where you have low quality here and medium, high, medium, and then the viewer changes their viewing direction to over here instead, then they'll see the low quality video. So if the system doesn't adapt quickly enough, this will make the viewing experience worse for the viewer. And this is very content specific and can be very hard to predict. It requires a lot of fine tuning in the system or in your algorithm. So what I mean by content dependent is that it can vary a lot between different types of videos. So for example, we have 2 graphs here where the left one, there's a lot less variation in the pitch angle and yaw angle from the center of the video compared to this one where there's a lot more variation. This can allow for specialization. If you do know this beforehand, then you can customize the algorithm to suit it better. So the main contributions of this paper is a 360 video player emulation tool that enables development of prefetching algorithms and quick iteration as a result of real-time downscaling and emulation of video tiling. A multi-step evaluation process that allows for calculation of frame-based metrics, analysis of playback metrics, and an analysis of viewers' head movements. Moving on to the emulator. So this is the design of the emulator. It's designed to be both modular and extendable so that you can easily implement your own algorithms and bandwidth estimations, for example. So this part here, as we can see, is the part where we implement the prefetching algorithm, and this is where would be implementing a new bandwidth estimation. So this is a flow chart showing the general frame-by-frame operation of the emulator to give you an idea how it works really and in what order it performs everything. So it starts with requesting and then checks if there's an active download, and if not, it starts the new download and then pauses if the buffer is empty. The network simulation of the emulator works one chunk at a time, and it uses an exponentially weighted moving average for estimation with a weight of 0.33 given to the most recent sample. The video manipulation of the emulator uses downsampling to group and average the pixels, as can be seen in the figure. This is performed on a GPU to ensure the real-time demands on the emulator. It also emulates the tiles, so there's no splitting the video files, as well as the chunks to again avoid splitting the video files. And no encoding is needed as the downscaling is done in real time. The metric logging logs several things. First and foremost, the stall start time. So if a stall event occurs, it logs when it starts and for how long the stall was. The user head movements are recorded as well. The video chunk and tile quality. So what chunk is requested by the requester. So if you have 4 tiles and 2 of them are in high quality and the other 2 are low, that gets logged. And then the tile, what tile is in focus by the viewer, so what's directly in front of the viewer in the video. And then the quality level of the tiles in view. So if there's 4 tiles in the view, 4 qualities will be logged. The player operates in 3 modes. We have the evaluation mode. This records the metrics using a human subject. And then the recording mode, which records a video of the user's viewport and from the previous steps without any stalls that might have occurred in the first step. And then we have the baseline, which does the same as the previous, but in the maximum quality instead of the quality actually viewed by the viewer. And this is what allows us to use frame-based quality metrics such as a multi-scale structural similarity, and also enables playback of a user's experience, so you can view back what the viewer actually saw if that interests you. Let's move on to the evaluation process. So the evaluation process works mostly identical. Well, it uses the first 3 steps of the emulator, and then you calculate the frame-based metrics at the end. For example, using VQMT, where you have the recording and the baseline stage as the input to the tool. And we performed an example evaluation. So to start, we had to set some settings in the emulator. We need a target resolution, so we selected 4K, which was the source material resolution, and then 1080p, 720p, and 480p, and none, of course. So we downscale that video, and we get some MMSys values for each of the resolutions, and then we convert that to an emulator equivalent using the block size, getting rough estimates of the same average value. And then we need a bitrate for the network emulation. And these values were set using average values by YouTube. So for the network, we used 1 bandwidth trace. This is the bandwidth trace used. The line here shows the average. And we had 4 network conditions, poor, with an average of 2,500 kilobits per second, fair average of 5,000, and good average of 10,000. So these, and capped, which is average of 10,000, but it's capped to 6,000. So these network conditions are using the same bandwidth trace as seen here, but this average is just multiplied to get to the value we want. We use two types of videos. The first one is a write type video, and the second one is an exploration type video. You can see you saw these figures earlier. You can see the difference in expected deviation or viewing angle of the viewer. Next, the algorithms used. We started off with a baseline algorithm, which we call non-biased. It fetches the same quality in all directions, and it gets the highest possible quality given the network conditions. So it works similar to the auto function on YouTube, for example. And then we have a tile-based greedy algorithm. It assigns weights to a tile based on the view, based on the distance from the viewpoint of the viewer. And then it has an adjustable A parameter that adds weight to missing tiles. So this is the aggressiveness parameter. So we have two values for this in our evaluation. So A equals 200 and A equals 0. So the 200 one is we call intermediate, and the 0 is the aggressive one. Here we can see an example of how the algorithm might operate. It starts by fetching quality level 2 in front of the viewer, and then adds quality level 1 to the left, quality level 1 to the right, some more quality in front of the viewer, and then some more quality to the left, and then we're out of bandwidth. So this is what gets fetched. So let's get on to the evaluation results. And so here we can see the video quality frame by frame for multi-scale structural similarity for the three algorithms. And we can see that aggressiveness impacts worst and best case quality. Here you can see the higher values for the intermediate and aggressive algorithms, but also the lower values as well. And the drops in multi-scale structural similarity correlates with missing tiles. So the red X's here in this graph indicates that some tile in view was of quality level 0, so it was just black for the viewer. Meanwhile, so you can see these three green lines here that correlated with the previous graph. And in this graph, this happens too often. Here we can see the average MSIM scores for the full duration of the video. And we can see that an intermediate algorithm performs better under poor and fair network conditions, as well as for ride videos. In regard to the percent above low, so the low reference number seen earlier. And then we have the aggressive performs poorly in regard to the 25th percentile of MSIM scores, which we can see in these figures here. It's a large difference compared to the worst of the other two. So better performance for ride videos is logical, as it is less likely that the focus will change, and therefore aggressively fetching in front of you makes sense. Head movements. See, there's less head movements for the aggressive algorithm, especially with the lower bandwidths. As you can see here, there's a large difference. And then we have the others. These are just some outliers, but yeah, it's always the least, or almost always the least amount of head movements. This is likely due to missing tiles or relatively poor video quality compared to the tiles next to it, disincentivizing a change in viewing direction and making the viewer think twice before looking in a direction. So this highlights the importance of having a user in the loop. Conclusions then. The paper presents a real-time emulation framework, 360 video that captures metrics valuable for evaluation, and a multi-step evaluation process that allows for the calculation of frame-based quality metrics. The modular design allows for speedy implementation and modification, and the evaluation results, while not conclusive, highlights the importance of including a user when designing and evaluating prefetching algorithms. Thank you for listening. The source code for the framework is available at the GitHub link with the paper.